Okay, so we will continue with the tutorials on Prandtl-Meyer expansion. So, I have a flow and it turns smoothly to some angle. So, this is a smooth curve. So, it's so let us take M1 to be 1.2 and M2 to be say 2.5. Find the turn angle. Okay. So, we assume Prandtl-Meyer expansion here, meaning the turn is without entropy change, or turn is isentropic. Okay. So, there would be a Mach wave here, then there would be another Mach wave here. So, there would be a series of Mach waves all emanating from an imaginary point somewhere here. Okay. So, you make a small turn at every location. Okay. So, the turn angle is very small at each of these Mach waves. Now, from whatever we have learnt, the final Mach number, because we have integrated d nu. So, the final values are going to give are the important quantities to get your turn angle, because you have integrated from nu 1 to nu 2 d nu, and I do not care what happens in between. So, all I bother is the first one and the last one. The first one and the last one depends on the Mach number of the first one and the last one. So, all I need to find is nu 2 and nu 1 to get the delta S, delta theta. Okay. So, this is associated with 2.5, this is associated with 1.2 for gamma equals 1.4. Okay. So, it is a pretty straightforward question. So, all you need to do is take that quantity. 1.2 is something which we had just now seen to be 3.558 minus 2.5 is 39.124 is my turn angle. So, now the same question, if I have a scenario like this, which is the flow that is going inside the surface like that, I would have a compression wave. M1 is 2.5, the turn angle is same as what we obtained earlier, which is 35.6. What would be my M2? So, what would be my M2? So, what I know is nu 2 is nu 1 plus delta theta, and delta theta is positive for expansion, negative for compression. So, what I have is nu 1 is associated with m1, which is 2.5, plus delta theta is 35.6. Yeah. Minus. So, nu 1 is 39.124 minus 35.6. You would get around 3.524. So, the Mach number associated with nu of this is 1.2. So, question 3. I have a turn which is 10 degrees, m1 2.5. This is case 1. Case 2, again the turn angle is 10 degrees. One is a sharp turn, the other one is a smooth turn. M1 is 2.5. Find Mach number after the turn. For both the cases. Okay. So, in the first case we have a shock, in the second case we have a Prandtl-Meyer compression. Okay. So, oblique shock. M1 is 2.5, theta is 10. So, my beta from the theta beta chart, .32 degrees, and I can find my M1n, which is M1 into sin beta. Then I would find M2n from the shock tables, normal shock tables, and I get M2 as M2n divided by sin beta minus theta, which is 1.332, and the 0.776, and my M2 is 2.07. For Prandtl-Meyer compression, my M1 is 2.5. So, my nu 1 is 39.12. Nu 2 is nu 1 plus delta theta. So, 39.12 minus 10 degrees. So, this is 29.12, which in the table would give me M2 is approximately 2.08, correct? okay, approximately 2.11. Okay. So, the Mach number is not very different from what you get from this. So, your P 02 by P 01 for this particular Mach number 1.2, if you look at the tables, 1.32 P02 by P0, this thing is 0.9993, and P2 by P1 is going to be 1.5. Okay. 1.32. Point, okay, 0.96, 0.996, and this is 0.8 something, correct. Whereas, what would be the P02 by P01 here and P2 by P1? This is going to be 1 because it is an isentropic flow, you know the stagnation pressure is going to be the same, and P2 by P1 will depend on your Mach number, which is P2 by P02 into P02 by P1. So, this will depend on your Mach number M2, this will depend on your Mach number M2. So, this is going to be P02 by P0, look at the isentropic tables for M2, which is 2.11, 2.11, P by P0, 2.11 is 0.08, 0.108, correct, and for M1, which is which is 2.5, 2.5 P0 by P by P0 is 0.55, 0.0585, correct. So, this is 1.846. Okay. Now, we can extend this things to your under expanded nozzle. So, in the slide which I have shown here, if I take the first picture, there is a normal shock that is sitting at the exit, which is the case where PB same as PB critical 2. Now, if I decrease my PB further, the shock is pushed downstream, then you have a scenario where the shock reflects with another shock and also form something called the Mach reflection. And if I decrease it further, then you move to the region called the under expanded nozzle. So, in the under expanded nozzle, the flow would try to expand further, and that is what is shown in the second picture here. So, here you have an expansion fan. So, these expansion fans are formed at the edge of the nozzle where there is a sudden expansion. So, the flow tends to turn, okay, turn this way because of the expansion, and then it has to come back to the other direction to pressure equalize the pressure. So, it forms structures like this where you have expansion fan at the tip of the nozzle, whereas in an under expanded in an over expanded case you have shock at the tip of the nozzle. Okay. You could try to evaluate what happens if you know the pressure at the exit of the nozzle and some pressure at the other location. You could see the deflection angle and see how the flow is turning in a direction which is not wanted, and to bring it back to the position where the flow direction is same as your axis, nozzle axis, you need some kind of deflections happening with expansion fan as well as shock and the combination of those. Okay. So, we will try to do one problem related to that and see how it is being deflected. So, what I am going to do is, I will have an under expanded nozzle. Okay. So, under expansion means I have some kind of expansion happening after the nozzle. So, it is under expanded and it is trying to expand it further once it goes out of the nozzle. And so, this is region 1, this is region 2. Assuming symmetry, there would be some other expansion happening here, it would be region 3 and so on. So, we will do a small problem in which this pressure is 200 say kilopascal, and this is let us say 100 kilopascal. What is the direction of flow in region 2? So, instead of going it straight outside the nozzle, it is deflected, okay, to some angle. So, what is the direction? What is the angle at which it is directing? So, the fluid comes and then it is deflected this way. So, what is this theta? This is the question. So, the given quantities are the pressures and Mach number at the exit is 2. Now, you have to assume few things, because the Mach numbers are changing all along this region. If you want to do the 1D analysis, what we have been doing, I will have to assume Mach number 2 to be same everywhere, and then in the region, this particular region, there I have to assume Mach number to be the same, and then only I can do this particular problem if I want to stick with 1D relation. Otherwise, you have to solve the full set of the so called momentum equation, which is our Navier-Stokes equation. So, what I will do is, so I have an oblique expansion fan here. M1 is 2, this pressure is 200, this pressure is 100 kilopascal, flow comes and makes a turn. What is the direction of the turn? So, P0 we can evaluate I can find P by or P1 by P01 from the isentropic tables or from the relation that which by now we should have by hearted, which is 0.138, from which you can get your P01. Now, this is an expansion, Prandtl-Meyer expansion, that is an isentropic flow. So, your P01 is same as your P02. Eh? This is 200. 156, okay, kilopascal. Now P2 is given, so P2 by P02 is 100 by 1562.5, which would give me an M2. From which I will get an M2, which is around 2.44. Okay. So now I know my M2 to be 2.44. If I know my M1 and M2, I can always get the angle at which it turned. So the angle at which it turns is nu2 minus nu1 equals delta theta. So nu2 for 2.44 minus nu1 for 2 from the Prandtl-Meyer expansion. How much? Around 11 degrees. So in the jet, so the velocity vector as it encounters the expansion fan turned a degree of angle of 11 degrees to this. Okay. Here also, if assuming symmetry at the center line, here also the flow would turn 11 degrees. Okay. So it is going out in the and that is one reason why most of the under expanded jets have jet width much larger than the nozzle diameter, and because of the periphery of the jet that is coming out, there will be a deflection from here and you will have series of expansion fans and shocks. Okay. Okay. Now we will end the discussion on Prandtl-Meyer function with one simple problem on external flows, which is it's a flow past a flat plate at some angle. At some angle of attack. So I have a flat plate, this is the flow direction, flat plate length is C, and it's facing a mark of say 2. Okay. So what is the lift generated. Or the lift coefficient. So, you have to find the CL, coefficient of lift. So, what is lift? Lift is nothing but the pressure difference which is acting on the top and bottom of the plate. So, related question will be, what is the pressure difference between top and bottom surface. Okay. To do this problem, we have to identify that when you have a plate like this, when you have a flow that is approaching this particular thing, in the top surface there is a turn which is an expansion. So, there will be an expansion. At the bottom surface there is a compression. So, there will be an oblique shock. So, this would be Randall-Meyer expansion. This would be an oblique shock. Obviously, when there is a shock, P2 lower is going to be greater than P1 lower, whereas your P2 upper is going to be less than your P1 upper, because it is an expansion. So, obviously, this pressure is going to be more and this pressure is going to be less, and hence there will be a lift that is generated, and the coefficient of that is what is being asked to find. So, all you need to find is the P2 at the lower surface and P2 at the upper surface, and find the difference. Okay. And this angle is so the angle of attack is, say, let us take 10 degrees. So, this is 10 degrees. So, it is an easy problem. Find, you have M1 given for the lower surface, oblique shock, upper surface, expansion fan. Okay. M1 is given. So, it is easy to, it's very easy to find the other quantities as we had done before. Find for the lower surface, use theta beta m chart, find M1n, from M1 and theta, find beta from theta beta m chart, find M1n, find M2n from shock tables. Once you have M2n, find your M2 from M1n, M2n. Once you have M2, find your pressure difference, pressure acting on this thing, find P2 if P1 is non. Okay. Now, for the upper surface, there is expansion fan. m1 is given, so you can find nu 1, theta is given, so you can find nu 2, which will give you m2, and from m2 you can find your pressure difference P2, because P0 1 is same as P0 2 for the Prandtl-Meyer expansion. So, you can find your P2. The difference between P2 upper and P2 lower would be your force that is generated multiplied by the angle cos theta of this. So, that would give you the lift. Okay. So, that is the lift, and CL is nothing but lift by 1 by 2 rho u infinity square, which you can write in terms of Mach number. Okay. So, your lift will be delta P cos theta, which is your angle of attack. So, I will use a different letter alpha. So, angle of attack is alpha equals 10 into the area, which is L into 1, which is the area that is across along the perpendicular to the board, and your drag force is delta P sin alpha C into 1. Okay. So, this is the force per unit area multiplied by area. Okay. So, this would be the lift force and drag force, and you can find the appropriate coefficients if you know the density and velocity. Okay. So, that brings us to the end of the discussion on Prandtl-Meyer expansion. That also brings to the end of the course. So, so what is discussed in the course is the fundamentals of gas dynamics, where we have discussed isentropic flows, shocks and oblique shocks and expansion fans. So, this course is essentially for an undergraduate student, and we have skipped several advanced topics which is not meant for this particular course. Okay. So, whatever has been discussed is very fundamental, and how to do problems using gas tables is what we have discussed in the course, and thank you.